Hi, my name's Terry Brown. I'm a lecturer and mechanical engineer at the University of Technology, Sydney. Welcome to this engineering mechanics instructional video. In this video, I'll go through the process of determining the internal actions of a loaded structural member. Over here we have a picture of the structural member that we're going to analyse. It's built in at this end, so fully supported, and at this end here we have 3 point loads applied. So a force of 200 newtons acting vertically downwards, 100 newtons acting axially, and another 300 newton force acting transversely. So our task is to determine the internal actions. So we need to point out where we're going to calculate those internal actions. And in our diagram here, we've got this section here highlighted at 2 meters from the end. So that's the section that we're going to analyze today. So the first step in determining the internal actions is to take an imaginary cut through the section where we want to know those internal actions. So over here I've now drawn the structural member, but only from this point forward. So where we want to know the internal actions, from that section forward, and from there we start to look at equilibrium. So we put on our applied loads at the end, and then at our internal section here we must have internal actions that keep these external loads here in equilibrium. So if we start by looking at each of the equilibrium equations in turn, so here we'll look at some of the forces in the x direction. Note that on my diagram I've indicated what x is, and also of course y and z directions. Okay, so taking first of all some of the forces in the x direction equals 0, we can see on our diagram here that we have a 100 Newton force in the x direction, and that's all we have. So on our internal section here, we must have an internal equal and opposite force of n subscript x. And then of course we can write that equation out. So we have nx is equal to 100 newtons. So next we'll look at some of the forces in the y direction, so the vertical direction, and here we have a 200 Newton force. That's the only external load that we've got applied to this side of the structural member that we're looking at. So internally here we must have an equal and opposite force for equilibrium. So we can put that in, and then we can write our equation of equilibrium, and our internal shear force Vy is equal to 200 newtons. So now we'll move on to some of the forces in the z direction, and we have just the one force here, the 300 Newton force in the z direction. So at our internal section we must have a force equal and opposite to that. So we can draw that in, and again we have a shear force subscript z for the z direction, and write out our equation. Vz equals 300 newtons. Okay, so now we have our forces, internal forces for equilibrium, but we also need moments to be balanced for equilibrium. So now we'll start looking at the moment equations. So we have some of the moments about the x-axis. So looking at our x-axis here, we have none of these forces are causing a moment about the x-axis, and there's no applied torque or moment. So we can write that our internal torsional moment is equal to 0. Okay, so next let's look at some of the moments about the y-axis. So we have our y-axis here. What loads out here are causing a moment about that y-axis? So if we look at the force in the x direction, well, that passes through the y-axis, so that's not going to have a moment effect. The 200 Newton force is parallel to the y-axis, so that's not going to cause a moment. And all we have left is our force in the z direction, which is at a distance of 2 meters from our y-axis, so that's going to have a turning effect around this way, around the y-axis. So we'll need that. So for equilibrium, we need to resist that moment around this way, so our reaction moment, or our internal reaction moment, is shown in this direction. Note that when I draw the vector here, the vector moment, I show it actually as a vector. So this arrow here is not a force, that's just the vector direction of this moment here that we've applied. So using the right hand rule, so just a quick reminder of the right hand rule. Okay, so here looking at a right hand, if our moment is going around the axis this way, so our fingers here point in the direction of the turning, and our thumb points in the direction of the vector. So when I draw the vector moment, right, so I'll have the direction of the rotation, or the intended turning, and then I also show the vector direction. Okay, that's just to make it a little bit easier to see the correct direction of the moment in 3 dimensions. Okay, so let's now return back to the problem. So we can now write the equation. So my is equal to 300 times the distance there of 2 meters, so my is 600 Newton meters. Okay, now let's look at moments about the z-axis. So we have our z-axis over here. Which of these forces out here are causing a moment about the z-axis? So let's again start with the force in the x direction. So that again goes back and passes through the z-axis, so that will have no moment effect. The 300 Newton force here in the z direction is parallel to the z-axis, so that will have no moment effect about the z-axis. So all we're left with is this 200 Newton vertical force, and its distance is 2 meters. So it's perpendicular to the z-axis at a distance of 2 meters. So we can write in, or draw in, our internal reaction moment first, and then write the equation to calculate that internal moment about the z-axis. Okay, so we've now calculated all of the internal actions acting at this section on this back face shown here. We can also show these internal actions on the left hand side of the component that we're analysing. So firstly we took the cut through here and we looked at this side of the structural component and drew our internal actions on that exposed face. Now if we look at the other side of the component, we've got our exposed face here from our imaginary cut, and we can put on here our internal actions on that side of the structural component. So the internal actions here will be equal and opposite to these ones that we calculated over here. Okay, so let's go ahead and draw those on our diagram. So first of all, we have our force in the x direction equal and opposite to the one up here, and force in the y direction equal and opposite to Vy, force in the z direction equal and opposite to Vz, and our moment in the z direction equal and opposite to the one up here, and so on. So the moment in the y direction, and of course we have no torsional moment about the x-axis. So let's go and put on all the labels for all of those internal actions, and now we have a complete diagram showing the internal actions acting on this face here of our cross section. And of course now you can go ahead and make use of these in calculating the stresses at this cross section of this structural component. Okay, so next I'll show you an alternative method to get directly to the internal actions on this cross-section using the vector moment equation. So if we draw our cross-section again, and we write out our vector moment equation, which is m equals r cross f. The vector r is the distance from the point where we want to calculate moments to where the force is applied. So in this case, r is equal to 2I, right? So it's 2 meters in the x direction, which has the unit vector I. If you're unsure about what I'm doing here, I have another video on vector algebra that you can look at to refresh your vector operations and vector notation. Okay, so next we have to define the force as a vector. So we have 100 newtons in the x direction, so that will be 100I, and we have 200 newtons in the y direction in the negative sense, so minus 200J, and a force of 300 in the negative z direction, so that would be minus 300K. Okay, so next we need to just do that vector cross product. Okay, so we just start multiplying through. So first off we have 2I times 100I, so 200I cross I. Then next we have 2I times 200J, which will give us 400I cross J. And then we'll have 2 cross 300, or 2 times 300, I cross K. And I cross I is 0, so that becomes 0. 400 I cross J becomes K. And minus 600 I cross K becomes minus J. Okay, let's just have a quick refresher of the signs that you get from cross products. So if we have this circle here with I, J and K shown, when we do our cross products, if we go anti-clockwise, so I cross J, we get positive K, J cross K, we get positive I, and K cross I, we get positive J. If we go around the other way, I cross K, we get minus J, K cross J, we get minus I, and J cross I, we get minus K. So let's return back to the problem. So as I said, that becomes 0, minus 400K plus 600J. So that's moment about the x-axis, right? So our I unit vector indicates the x-axis. Right? So we determined before that the torsional moment was 0, so that corresponds. And then here we've got K, so that is the z-axis. So we've got 400K, right, 400 Newton meter moment about the z-axis, and 600J, which is my. And we can put all those on our diagram again, and you should see that what we have here corresponds, and what we have here and now drawn on our diagram corresponds to what we calculated previously using the equilibrium method. Okay, so that's it for this example. Hope you found that useful, and I'll see you next time. Thanks for listening.